In this BocaPhysics video, you'll see simulations on flux and Gauss's law. In this first simulation, you'll see the flux through a square. In this region of space, the electric field is uniform and is depicted by the arrows. Notice that the electric field is perpendicular to the square through which the flux is being calculated, and only the electric field lines that pass through the square contribute to the flux. Since the electric field is perpendicular and uniform, the flux is simply E times A, where A is the area of the square. In this next simulation, electric field lines pass through a box. Again, only the electric field lines that pass through the box contribute. But in this case, they pass into the box and they pass out of the box. Hence, the net flux is 0. Only if there were a source inside of the box would you have a non-zero flux. In this next simulation, there are two Gaussian surfaces drawn around a single point charge. It matters not how large the Gaussian surfaces are, the flux remains the same. To understand this, consider the electric field lines. Here we have 4 field lines that pass through a patch on the inner Gaussian surface. These same 4 electric field lines pass through the patch on the outer surface. Even though the area of the outer sphere is 4 times as large, the flux remains the same. Electric field goes as 1 over r squared, so therefore if our outer radius is twice as large, the electric field decreases to 1/4 its value, and therefore the flux remains the same. The yellow arrow depicts the normal to the surface, and the normal will always be in the radial direction. The next simulation is that of a sphere. The red denotes the Gaussian surface, and the yellow arrow is the normal. So any direction, the normal to the surface will always be in the radial direction. Gauss's law can be applied to systems where the charge density is only a function of the radius, as well as being applied to conductors. If you're investigating the electric field due to a wire or due to a cylinder, the Gaussian surface you want to choose is that of a cylinder. The yellow arrow is normal to the surface and will always be radially outwards from the axis of symmetry. Gauss's law can be applied if the charge density depends only on the radial distance. As long as it doesn't depend on the angle, and as long as your cylinder is long enough, you can apply Gauss's law. The final simulation is that of a charged sheet. The Gaussian surface you choose here is the pillbox. This pillbox extends a little above and a little below. We had a charged sheet of positive charge, the electric field would be pointing away from it. So it would be pointing up above the pillbox, and it would be pointing downwards below it. The effect of that is that you'll find that electric field is equal to sigma over 2 epsilon naught above, pointing above, and sigma over 2 epsilon naught pointing below. This concludes the Gauss's law simulation.